In this video I'm going to be talking about a particular type of LU factorization or LU decomposition called Cholseky decomposition. Okay, now Cholseky decomposition is more computationally efficient than standard LU factorization, but the caveat to this is we need to have a positive definite matrix. So it only works if your matrix A is what we call positive definite. Okay. Now the definition of a positive definite matrix is if X transpose A times X is positive for any X, for all X, so for any X is a vector, so in Rn. Okay, so that's the definition of positive definite matrix. Now what Cholseky factorization seeks to do is it wants to factorize your matrix A into the product of a lower triangular matrix L multiplied by the same lower triangular matrix L but transposed. So if you have a look at an example with a 3 by 3 matrix, A21, A22, A23, A31, A32, A33. Okay, so standard 3 by 3 example. Okay, so I'm going to have L11, 0, 0, L21, L22, I'm going to L31, L32, and L33. Note that unlike LU factorization, I haven't assumed that the main diagonal elements and L are all ones, so I'll show you why in a minute. So if we transpose this, okay, we'll have L11, L21, and L31. We'll have 0, L22, and L32, and we'll have 0, 0, L33. Okay, so that's what we're seeking to do. So we want these 6 values. So I've got 6 values here to calculate. So if I multiply these two together, I'll get L11 squared, I'll get L11 L21, and I get L11 L31. On the first row, on the second row, I'll get L11 L21, I'll get L21 squared plus L22 squared, and we'll get L21 L31 plus L22 L33, and finally get L11 L31, I'll have L21 L31 plus L22 L33, and finally I have L31 squared plus L32 squared plus L33 squared. Phew. Right, so after all that, that's what we'll get. Now what you notice about this matrix here is this is symmetric. So for example, the element in row 1 column 2 is the same as the element in row 2 column 1. So this means I only need to calculate one triangular region. So the main diagonal plus, let's say, the lower triangular region, that's 6 elements. Okay, so those 6 elements. If we have a look at the elements on the main diagonal, you can see they follow a pattern. So elements on the main diagonal, we have LJJ squared plus the sum of k equals 1 to j minus 1 times L jk squared. That's meant to be a k. Okay, so for example, if we take the third one, okay, so we have L33 squared, and then added to that we have L31 squared plus L32 squared. Okay, so that gives us that. Oh, one thing I have just made a mistake here. That should be A11. Okay, and for all other elements, so that's when so that's main diagonal. So that's main diagonal. For all other elements, okay, we have Ljj times Lij plus the sum of k equals 1 to j minus 1, so it's the same sum of Lik Ljk. Okay, so just test it on one of these. Okay, you'll see that that's correct. Right. Okay, so we want to rearrange those to give L as the subject. Okay, so if I rearrange those to give L as the subject, I'm just going to clear myself a little room here. Okay, so let's rearrange those. So what we have is we have a case where on the main diagonal, so from the main diagonal, if I rearrange this, okay, so subtract the summation from both sides and square root. So the square root of Aij minus that summation. Ljk squared. Okay, so that's where I equals j, so that's on the main diagonal. For all other cases, okay, we have, if I rearrange this, so I want to make Lij the subject, I'll have 1 over Ljj multiplied by Aij minus, and that summation, 1 to j minus 1. Just notice that looks like an equals, that's meant to be a minus. Lik Ljk. Okay, so we don't have any, unlike LU factorization, we don't have any U's to solve for, we just have L's. So, and we've only got 6. We've only got 6 to solve for it, so it's much more computationally efficient. Okay, so what I'm going to do is just go through an example. Okay, so let's see, this is example 6.9 in the notes. And the example was, we're presented with a matrix A, which is 4 minus 2 minus 4 minus 2, 10, 5 minus 4, 5 and 14. Okay, so this is positive definite. Take my word for it, or you can check it whether it is positive definite. A way to check it is, it's a positive definite matrix has to be symmetric and it has to have all positive eigenvalues. Okay, so what I'm just going to do over here is just rewrite the Cholseky, just to remind myself. So it's root of Aij minus that sum, k equals 1 to j minus 1 of jk squared. Okay, my writing's getting worse and worse, so I hope you can read it. If not, just check out the lecture notes where it's all typed out. J equals 1 to I minus 1 Lik Ljk. Okay, so as always, as with before, we go down each column. So first column, j equals 1. Well, for when I is equal to 1, we're on the first one, so L11 is equal to A11, and then this summation. But this summation is not going to count because I'm on j equals 1. So that's the root. That's the root of A11, which is root 4, which is obviously 2. So L21. Okay, so now I'm on this one because I'm in the lower triangular region. So that's 1 over L11 multiplied by A21, and then again this summation because j is equal to 1. That's not going to. The summation is not just going to be 0. So that's going to be 1 over 2, and A21 is minus 2, so that's minus 1. And L31 similar, so 1 over L11 times A31. So that's 1 over 2 times minus 4. Okay, so that's the first column done. On to the second column. So we'll only have 2 of these to calculate. So L22 is going to be the square root of A22 minus L21 squared. Right, yeah, all under the same square root. So it's going to be the square root of 10 minus L21 was minus 1, but square that, we get 1. So that's going to be root 9, which is obviously 3. And L32, this time we're in the lower triangular region, so we're using that one. So it's going to be 1 over L22 times A32 minus L31 L21. So it's going to be 1/3. A32 is 5. That's going to be minus L31 is, what was L31? Minus 2, so that's going to be plus 2 multiplied by L21, which is minus 1. So it's going to be 1/3 times 3. Got the 1 there. 1/3 times 3 is obviously 1. Finally, J equals 3. So we've got L, just the L33. So that's going to be the square root of A33. That's going to be minus L31 squared minus L32 squared. Okay, so A33 was 14 minus L31 squared, so that's going to be 4 plus 4, because that's a minus, it's going to be minus, and L32 is 1, so it's going to be minus 1. So that's root 9, so it's 3. So therefore our L matrix is 2 minus 1 minus 2, 0, 3, 1, and 0, 0, 3. Oh, sorry, 0, 0, 0, 3. Okay, so that's our Cholesky decomposition. We should really check whether that's correct. Okay, you can do that with all of these sort of algebraic questions. So we're going to check whether we got it right. So our L, just to remind ourselves, just writing it down again. So we reckon, I say we reckon, what we were trying to show, trying to decompose A into the product of two matrices, L and its transpose. So if we write down what L was, and the transpose of L, 0, 3, 1, 0, 0, 3. Okay, multiply these two together. Okay, so 2 times 2 is 4. 2 times minus 1 is minus 2. 2 times that is minus 4. Okay, on here we'll have minus 2. Minus 1 times minus 1 is 1. Plus 3 is 4. Oh, sorry, plus 3 times 3 is 10. So 1 plus 9 is 10, obviously. We have 2, so we'll have 2 plus 3 is 5. Okay, and we'll have minus 2 times 2 is minus 4. 2 plus 3 is 5. And finally we got 4 plus 1 plus 6, which is 14. Which, if you compare that to our original matrix A, you can see that it checks out. Okay, go on to talk a bit about how we can use Kraut's algorithm with Cholesky. So this is something we kind of refer to this as a Cholesky-Kraut algorithm. So Cholesky-Kraut. Okay, so remember we were trying to all of this is to do with solving the linear system AX equals B. We've decomposed A. Okay, so it's a lower triangular matrix. We decompose A using Cholesky factorization. So it's a so L is a lower triangular matrix multiplied by its own transpose. It gives us the gives us LLT. Okay, so as before, if we let Y equals L transpose X, so the steps are: step 1, solve. Oh, I've skipped a step there. So we let Y equals L transpose X, so therefore we solve for L Y equals B. So we solve for Ly equals B in step 1. In step 2 we solve for L transpose X equals Y. Okay. So if we look at an example, okay, this is taken from the notes. Okay, and this is example 6.11. And what we wanted to do in 6.11, we have our same matrix as I just used previously in the example. Our x, our unknown vector, and we've got our right hand side constant vector, which is in this case is -2, 49 and 27. Okay, we saw just now, but our L or Cholesky decomposition of that gave us L equals this matrix. Okay, so step 1 is we're solving for Ly equals b. So what we have is we have 2, 0, 0, minus 1, 3, 0, minus 2, 1, 3. Okay, and that's y1, y2, y3, and 27. Okay, so I've kind of laid out this the wrong way, but hopefully you can see. So we do that using forward substitution. So we've got 2y1 equals -2. So we'll see y1 equals -1. Okay, on the second one we have 3y2. So the coefficient of y2 is 3. So y2 is going to be 1/3 times 49 minus, but that's a -1, so that's going to be plus y1, which is a minus. Okay, yes, so that's going to be -1, so that's 48, so that's going to be 16, and y3, coefficient of y3 is again 3, so you have 27 plus -1, so it's plus 2, minus 16, which is going to be, oh hang on, have I got a, just double check my signs, so I've got -2, but that's going to be a +2, that's going to be, yeah, so that there is going to be a -2. Now 27 minus 18 is 3. And yeah, it's 9 divided by 3 is 3. Okay, so that was the first step. The second step is to solve, I was going to say u then, L transpose x equals y. So L transpose is 2 minus 1, 2, 0, 3, 1, 0, 0, 3. And that's given us our x values, and on the right hand side we're going to have our y values, so -1, 16 and 3. Okay, we're going to do this using back substitution. Right, so 3x3 equals 3, so x3 is clearly 1. X2, coefficient of x2 here is 3, so that's going to be 1/3. Okay, 16 minus whatever x3 is, so it's going to be 15, so it's going to be 5. And down here we've got x1. Coefficient of x1 is 2, so it's going to be 1/2. -1 minus plus -1 minus -1, so it's +1 times x2, which is 5, minus 2 lots of x3, which is 2. So that's going to be 2/2, which is 1. Okay, so that's how we use the Cholesky-Kraut method for solving a linear system. Remember, but we can only use the Cholesky method if this is a positive definite matrix.